Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss Einstein's theory of specific heat in solids. Let's begin. Specific heats in solid is explained by Dulong and Pettis. According to Dulong and Pettis, specific heat at constant volume is equal to constant Cv is equal to 3R, means the specific heat is independent of temperature and the nature of the solids. But Dulong and Pettis law can't explain that specific heats of solids at low temperatures. That limitations of Dulong and Pettis law can be overcome by Einstein's theory of specific heats in solids. So, according to Einstein, he assumed some points to show how specific heats of solids can be explained at low temperatures. Some assumptions: all atoms are identical, independent simple harmonic oscillators, and that simple harmonic oscillators vibrating with the same natural frequency. But in case of Dulong and Pettis law, that point is same, that is simple harmonic oscillator, and Dulong and Pettis law based upon the classical theory. But in case of Einstein's theory, he proposed the quantum theory to show the specific heats in solids. Here that simple harmonic oscillators are classical in case of Dulong and Pettis law, but in case of Einstein's theory, the simple harmonic oscillator we prefer as quantum. And every crystalline solids consist of n atoms, and each atom is equivalent to 3 mutually perpendicular Planck oscillators. Each atom has 3 mutually perpendicular to Planck's oscillator. What is Planck's oscillator? A Planck's oscillator is an oscillator which can absorb or emit energy in amounts. What amount? That amount is integral multiple of Planck constant s times to that of frequency of the oscillator, frequency nu, and follows the Planck's law for blackbody radiation on the basis of Bose-Einstein statistics. Here we use Planck's oscillator, that is based on quantum oscillator. Next assumption point: the energy spectrum of Planck oscillator is discontinuous. Energy spectrum of Planck's oscillator is discontinuous. But as we assumed in case of Dulong and Pettis law, that energy spectrum is continuous. Therefore, when we calculating the total energy, we just integrate. But in that of case, when we calculating the total energy, instead of integration, we use summation, as the energy spectrum is discontinuous, but has discrete values in accordance with quantum theory. Next assumption point: each of 3n harmonic oscillator, since it has 3 mutually perpendicular Planck oscillator, so each of 3n harmonic oscillator have quantized energy, and that quantized energy is given by U of n is equal to n plus half s nu, whereas n stands for 0, 1, 2, 3 like this, s for Planck's constant, nu for frequency. Let me derive what will be the total energy. and then specific heat at constant volume. Derivation. The average energy of such oscillator in the sense Planck's oscillator, which is quantum oscillator, is given by the relation U bar, average energy, is equal to summation over n from 0 to infinity. Instead of integration we use summation, as the energy spectrum are discontinuous, but in case of de Long and Petit's law it is continuous, therefore we use integration using the limit minus infinity to plus infinity. Un e to the power minus un by kBt divided by summation over n from 0 to infinity e to the power minus un divided by kBt. Now we put the value of un in that of equation, that is equation number 1, that is equation number 2. Putting the value of un in equation number 2 from equation number 1, we get the average energy U bar is equal to summation over n is equal to 0 to infinity, in place of un, that is n plus half h nu, n plus half h nu into e to the power minus n plus half h nu divided by kBt. Whole divided by, again in place of un we substitute that value, summation over n from 0 to infinity e to the power minus n plus half h nu divided by kBt. Let us substitute here, substituting minus h nu divided by kBt, kB as Boltzmann's constant, we have already known it, is equal to x. Say using that substitution, that equation changes to U bar is equal to h nu summation over n from 0 to infinity n plus half e to the power n plus half x divided by summation over n is equal to 0 to infinity e to the power n plus half x. Next, or u bar is equal to h nu. We expand it of that of summation, first putting n is equal to 0, then n is equal to 1, 2, like this. When we putting n is equal to 0, it will be half e to the power x by 2, n is equal to 1, 3 by 2 e to the power 3x by 2. Next, first n is equal to 0, then n is equal to 1, then n is equal to 2, that's 5 by 2 e to the power 5x by 2 plus dot 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 divided by, again that summation is expand by putting n is equal to 0, 1, 2, 3, like this. We have e to the power x by 2 plus e to the power 3x by 2 plus e to the power 5x by 2 plus dot dot dot. Which is equal to h nu. That term, the overall term, can be written as derivative of d by dx of log base e having e to the power x by 2 plus e to the power 3x by 2 plus e to the power 5x by 2 plus dot dot dot. Taking first term e to the power x by 2 log e to the power x by 2 of base e, when differentiate with respect to x, we have 1 divided by e to the power x by 2 into derivative of that e to the power x by 2, that is half e to the power x by 2. So that term is obtained. Similarly, the entire term we obtain by taking the differentiation of that particular term. So instead of that term, we write d by dx of log of this is equal to h nu d by dx of log of base e. Here we take common e to the power x by 2. So inside that of bracket, we obtain 1 plus e to the power x plus e to the power 2x plus dot dot dot. Next, using the formula log a into log b, that is log a plus log b is equal to h nu d by dx log e to the power x by 2 base e plus log 1 plus e to the power x e to the power 2x plus dot 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 base e. So what will be the value of log of that term? Look here, log of 1 plus e to the power x plus e to the power 2x plus dot 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 having base e is equal to we have log 1 minus e to the power x to the power minus 1, 1 minus e to the power x to the power minus 1. When we expand binomially, we obtain that term 1 plus e to the power x plus e to the power 2x like this. So instead of that log, we use this one, log of a to the power minus m. So that term minus m is multiplied to this minus m log of that term. So minus 1 log 1 minus e to the power x. That substitution is used. We have h nu d by dx log of e to the power x by 2. So that x by 2 is multiplied to this term, that is x by 2 log e base e is equal to 1 minus, instead of that we use minus 1, that is log of base e 1 minus e to the power x is equal to h nu derivative of x by 2, that is half, minus the derivative of that log term. So minus 1 divided by 1 minus e to the power x. So again minus minus plus, plus e to the power x divided by 1 minus e to the power x, derivative of that log term, is equal to h nu half plus, let me write e to the power x divided by 1 minus e to the power x as 1 divided by 1 minus e to the power x divided by ex. So just substituting that value 1 minus e to the power x, 1 divided by 1 minus e to the power x divided by e to the power x. For that term we use 1 divided by 1 divided by e to the power x minus e to the power x divided by e to the power x. So we write 1 divided by e to the power minus x minus 1, that is 1 divided by e to the power minus x minus 1. Again substituting x is equal to minus hf by kbt, as we substitute in this, x is equal to h nu divided by kbt. So it will be h nu half plus 1 divided by e to the power h nu divided by kbt minus 1. Now separating the individual terms, that is half h nu plus h nu divided by e to the power h nu by kbt minus 1, that is for u bar, average energy. As you know, there will be n number of atoms present in that of crystal. If n is the number of atoms present in the crystal, then it is equivalent to 3n oscillators. each one is perpendicular to 3 number of Planck's oscillators, mutual perpendicular to 3 number of Planck's oscillator, therefore that is equal to 3n oscillators. So that the total energy becomes, so total energy U is equal to 3n into average energy U bar. So 3n average energy, that is half h nu plus h nu divided by e to the power h nu by kBt minus 1, that 3n is multiplied 3n h nu by 2 plus 3n h nu divided by e to the power h nu kBt minus 1. That is the total energy U. Now specific heat at constant volume. Now specific heat at constant volume, that is Cv is equal to du by dt at constant volume, V is equal to constant. So d by dt, total energy U is put, that is 3n h nu divided by 2 plus 3n h nu divided by e to the power h nu by kBt minus 1. Its differentiation. So first term, there will be no such term of temperature, so that will be 0, plus next term a differentiation d by dt of 3n h nu divided by e to the power h nu by kBt minus 1. Or Cv is equal to, here 3n h nu is the constant term, that is outside 3n h nu, next d by dt of that term as e to the power h nu by kBt minus 1 to the power minus 1. Therefore its differentiation is equal to 3n h nu into differentiation as minus e to the power h nu by kBt minus h nu by kBt t square 1 by t into t divided by e to the power h nu by kBt minus 1 whole square, that is the differentiation of that term, is equal to write it rearranging the terms as minus minus plus 3n, we multiply a term kb and divide a term kb. So inside that of term, the bracket h nu kbt whole square, there will be no such change. E to the power h nu by kbt divided by e to the power h nu by kbt minus 1 whole square. Again we use a term in place of h nu, that is theta e into kb, theta e into kb, where theta e, that is Einstein's temperature, Einstein's temperature. So that equation is written as 3n kb. In place of h nu we substitute theta e into kb, 1 kb cancel out, that is theta e divided by t whole square into e to the power theta e by t divided by e to the power theta e by t minus 1 whole square, that for Cv, specific heat at constant volume. Equation number 3. Equation number 3. So mathematically we show, taking the average energy of that of oscillator, expanding the terms, mathematically we solve it. The average energy we obtain, next total energy 3n into that of average energy with the total energy, next specific heat at constant volume Cv, that one. Let we calculate that result by using high temperature and low temperature. There is two special situations. First one, at very high temperature, at very high temperature, when the temperature is very high, that is T is much greater than that of Einstein's temperature theta e. Therefore theta e divided by T is very less than 1. Therefore e to the power theta e by T can be expanded as 1 plus theta e by T plus half theta e by T whole square plus dot is equal to 1 plus theta e by T, neglecting the higher order terms, neglecting the higher order terms. Now, so here e to the power theta e by t is equal to 1 plus theta e by t. That substitution is used in equation number 3. Therefore, Cv we obtain is equal to 3n kb theta e by t whole square 1 plus theta e by t in place of e to the power theta e by t we substitute 1 plus theta e divided by t whole divided by theta e by t whole square. Therefore, Cv is equal to 3n kb plus 1 theta e by t whole square cancelled out, that one is multiplied. Next 3n kb whole into theta e divided by t. When t tends to infinity, then theta e by t tends to 0. Therefore, that particular equation can be written as, hence Cv is equal to 3n kb is equal to 3r, or Cv is equal to 3r. This result is same as the Dulong and Petit's law. Petit's law, which confirms that specific heat of solids is independent of temperature. The specific heat of solid is independent of temperature. Thus, we can say Einstein's theory on specific heat is satisfactory. As the high temperature limit, because the quantum aspects become irrelevant. Now, at high temperature it confirms the specific heat will be constant, but then what happened at low temperature? At low temperature, what will be the situation? At low temperature, when the T is very less than Einstein's temperature theta e, then we obtain e to the power h nu divided by kBt is greater than to that of 1, so that e to the power theta e by kBt is equal to 1 minus e to the power theta e divided by t. By using these substitutions to that of equation number 3, So the expression for Cv becomes Cv is equal to 3 nkb theta e divided by t square e to the power theta e by t whole divided by e to the power 2 theta e divided by t, or Cv is equal to 3 nkb as r, next theta e by t whole square into, that is exponential e to the power minus theta e by t, that to this side it will be negative, theta e minus 2 theta e, that is minus of theta e. So in low temperature, that is 3R into something. So when temperature T approaches to 0, the exponential term e to the power something, that is e to the power minus theta e by t, that approaches to 0, that tends to 0. Therefore the specific heat Cv is equal to 0. So at low temperature Cv is equal to 0 is explained by using Einstein's theory of specific heat in solids. This is at very high temperature, that is same to that of DeLong and Petit's law. That one is for low temperature. Then what be the limitations of that of Einstein's theory for specific heats in solids? So the limitations, as we say, when taking the graph between Cv and temperature for diamond, here is the 3R, for diamond it will be just like this, but by taking that Einstein's theory it will be seen that way. So the limitations for Einstein's theory of specific heats in solids: experimentally Cv is directly proportional to the cube of the temperature, but in Einstein's theory Cv is directly proportional to e to the power minus theta e by t. This is experimental results, but this is the theoretical way as we show in that of Einstein's theory in specific heats in solids. This region, that is also simplified by using another theory, that is known as Debye model of specific heat in solids. Next limitation, here we write a assumption that all atoms are identical and independent simple harmonic oscillators vibrating with same natural frequency, but actually these atoms are not independent simple harmonic oscillators, they are coupled harmonic oscillators, and each has different own frequencies. Okay. In reality, the atoms forming harmonic oscillators are coupled together, with wide range of frequencies, So, that assumption is not valid. These two are the drawbacks of Einstein's theory in specific heats of solid, and that one is a graph that shown how Einstein's theory of specific heats in solid explain in case of diamonds. That is a theoretical value, this one is the experimental value. So, with the help of this video lecture, we understand the concept of Einstein theory of specific heat in solids, some assumptions deriving, first taking average energy, mathematically we proceed, and finally we take the average energy, then total energy, then specific heat at constant volume Cv. From Cv we show what it will be at very high temperature, that result for very high temperature Cv is equal to 3R, which is same as de Long and Petty's expectation. Next, at low temperature, that can't explain in de Long and Petty's law, but it explained by using Einstein's theory of specific heat in solids, Cv will be 0. Then the limitations of Einstein's theory of specific heats in solids, two limitations. Experimentally we show Cv is directly proportional to Tq, but according to Einstein it is directly proportional to e to the power minus 3 by T. So, that can be further simplified by using Debye model of specific heats in solids. And another limitation is, in reality the atoms forming harmonic oscillators are coupled together with wide range of frequency, but we assume that they are independent simple harmonic oscillators and having equal and identical frequencies. So, the assumption is not valid in that particular situation, and a graph that shown how that holds good for diamond. So, with this useful and informative notes, let me wind up this session. Thank you.